Hello everyone from Math 2000, it's linear algebra. It's Professor Winson here again with a video on your ZyBooks Section 4.3 on properties of determinants. Now, in sections 4.1 and 4.2, we've been introduced to the determinant of a square matrix and how to find the determinant of a square matrix. Now for a 2x2 and a 3x3, there were some pretty reasonably simple formulas, methods to find the determinants of a 2x2 and a 3x3. But then for any general square matrix, we also saw the method of cofactor expansions or minor expansions with alternating signs. In this section, we're going to see how a third possibility. We're going to see yet another way of finding the determinant of a square matrix. And this will be through use of elementary row operations. Hopefully you recall those, how you took a matrix and transformed it into a row equivalent matrix using elementary row operations. To put a matrix in echelon form or reduced echelon form. So we're going to do that here. And we're going to see how performing a row operation affects the determinant of a matrix. And then we'll also see how you could also do something similar with column operations. But for the most part, I'm going to stick to doing elementary row operations. Alright, so you have the section summary. I'll let you read that, a couple objectives. Alright, so I mentioned elementary row operations. Now here's a little, this is going to be very important, these three lines. How do the row operations affect the determinant of a matrix? Alright, so the effects of elementary row operations on the determinant of a matrix are shown below. So suppose A and B are n by n square matrices, and K is a scalar, right? Some real number. So number one, if a multiple of a row of A is added to another row of A, remember that's one of the row operations, where a multiple of one row is added to another row to make a new matrix called B, then the determinant of B will be exactly the same as the determinant of the original matrix A. Alright, so this first line is saying that if you take a multiple of one row and add it to another row and replace that other row, perform that row operation, the determinant will not change. Okay? Number two, if two rows of A are swapped, are interchanged to make a new matrix called B, right? So you just switch two rows of A to make a new matrix B, then the determinant of the new matrix will be the opposite of the determinant of the original matrix. So the determinant of B will be the opposite of the determinant of A. So this tells us that switching two rows will give you the opposite determinant. Right? We'll multiply the determinant by -1. And number three, if a row of A is multiplied by a scalar, right? So remember that was another operation that we could do, was multiply a row by some number. If you do that, you'll create a new matrix called B. The determinant of this new matrix will be K times the determinant of the old one. So if you take an original matrix, multiply one of the rows, just one of the rows, by K, the new matrix you create will have a determinant that is K times the old determinant. Alright, so I'm actually going to take you through examples here. Now I'll take you through an example with like a 2x2 matrix. Okay, so here's a 2x2 matrix that I just made up, threw this out here. First row has 1, 2, the second row is 3, 7. All right, now the determinant of this matrix is pretty easy. Right? The determinant of A here is 7 minus 6, right? So the determinant of this matrix is just the number 1, right? All right. So now what I'm going to do in part 1 is I'm going to take matrix A here. We'll start with matrix A, and I'm going to perform a row operation. Okay. So this first one, I'm going to take a multiple of one row and add it to another row to create a new matrix. So let's say I take 4 times the first row and add it to the second row, and this will produce a new second row. All right. Now that will create a new matrix which we'll call B, right? Just to stay consistent with the book. Before I was calling it like A prime, right? But this will create a totally new matrix. B. Now notice the only row that will be changing is row 2. So row 1 with 1, 2, that'll stay the same. And I'm going to be changing row 2 by multiplying the top row by 4 and adding those to the row 2 entries. So 4 times 1 is 4, plus 3 is 7. 4 times 2 is 8, plus 7 is 15. All right, and let's take a look at it now. You see, I performed this row operation where I took a multiple of one row, added it to another row, and produced a new matrix. Now look at what's the determinant of this matrix. What's the determinant of B here? Well, it's 15 minus 14. So you see, it's still 1. It's equivalent to the determinant of the original matrix, right? Nothing changed. I mean, the look of the matrix changed, but the determinant did not. Okay, so adding a multiple of one row to another row to produce a new matrix doesn't change the determinant. The next one they mentioned, right? The other was just switching rows. Right, so again, I'm going to start with matrix A. Right, start with this matrix here, and I'm going to perform an operation, a row operation, where I just switch the rows. Right, so row 1 switches with row 2. And this will create a new looking matrix, right? We'll call this matrix B again. And if I just simply switch the rows, that'll be 3, 7 up top, and 1, 2 on the bottom. Right? 1, 2 for the second row. All right, now let's take a look at the determinant of this new matrix. Right? What's the determinant of B? Right. Well, it's 3 times 2, 6 minus 7. 6 minus 7. That's negative 1. Do you see how it's the opposite of the original determinant, right? It's the opposite of the determinant of A. Right? The determinant of A was just 1. When I switch rows, I get the opposite determinant, negative 1. All right. So again, just to recap, these first two, adding a multiple of one row to another row doesn't change the determinant. Switching two rows gives you the opposite determinant. All right, and then the only other row operation we haven't seen yet is just multiplying a row by a scalar, multiplying a row by a real number. All right, so again, I'm going to start with matrix A. So I'm starting with this 1, 2, 3, 7 up here. We're going to perform an operation. All right. Now this time I'm going to I'll say, let's multiply the second row by 3. So I'm going to do 3 times row 2. And this will produce a new row 2. Remember this operation of multiplying a row by a scalar. Now if I multiply the second row by 3, that's creating a whole new matrix, right? Again, since it's a new matrix, I'm going to call it something else, right? Like B here again. Now I'm not changing the first row, so the first row of B is still 1, 2. I am multiplying the second row entries by 3. So we have 9, 3 times 3, and then 21. Right. Now, what's the determinant of this matrix, this new matrix? Well, it would be 21 minus 2 times 9. 21 minus 18. That's 3. And this is triple the original. See how this is 3 times the original determinant. Okay. So hopefully just with this one example, right, again, it's a very small one, just a 2 by 2, but hopefully with this example you can see the effect of the row operations on the determinant of a matrix. And these apply to 3 by 3, 4 by 4, and so on, any square matrix. So one more time here, going through these. If I add a multiple of one row to another row, the determinant will not change. If you switch two rows, you get the opposite determinant. And if you simply multiply one row by a number, you multiply the determinant of the original matrix by that number as well. Right? The new determinant will be that number times the old determinant. Okay? All right. So let's take a look at their example. And then we'll maybe get into I think they have an activity after. Yeah. All right. So look at this example. Now we are told that the determinant of this 3 by 3 matrix is 40. And they're asking us to find, knowing this, find the following determinants. So you have two of them here. So part A, you have the determinant of this 3 by 3 with, 1, negative 1, 3, then 3, 2, 0, then 5, 0, negative 2. Now look, compare these. The third rows are the same, but you see how the first and second row are just switched? So if the determinant of this matrix up top was 40, and I just switched the rows 1 and 2, I'll get the opposite determinant. This matrix should have a determinant of negative 40, and they mentioned that here. Switching two rows gives me the opposite determinant, changes the sign of the determinant. Okay, and then again, how does this third one, this part B, how does this matrix compare to the original? Well, the second row is the same, the third row is the same. The first row, though, see how this first row, 6, 4, 0, isn't that just twice the first row here? So I would have taken this top matrix and multiplied the first row by 2 to get 6, 4, 0. And if you multiply a row by 2, if you multiply one row by 2, you'll multiply the determinant by 2 as well. So the determinant of this new matrix is this old one times 2. So it should be 80. And again, you can double check it, but it's just going to be 80. They explain it here. Okay. So let's take a look at this. So here is a 4 by 4 matrix this time. Now they are telling us, that the determinant of this matrix is 606. Now you could go through and do cofactor expansion or use your calculator, just to make it quicker, and see that the determinant of this matrix is 606. We're asked to find, all right, well, if the determinant of this matrix is 606, what would be the determinants of these, 4 by 4 matrices? All right, so look at this first one here, number 1. Same first row, same second row, same third row. The fourth row is different. And you see, in order to make this original row into this row, I would have to multiply this fourth row by a third. Right? If I multiply this fourth row by a third, that would give me this row here. So if I multiply this fourth row by a third, to get this new matrix would have a third of the determinant. Right? You'd multiply the determinant by a third as well. And a third of 606 is 202. So the determinant of this new matrix should be 202. Okay. So again, keep this this matrix here. This has a determinant of 606. Let's look at the second one. So I may be scrolling up and down a lot, but they got the same first row. Cool. They got the same third row. Also nice. Okay, it's the second row and the fourth row that are a little different. All right. But they're just switched. See, the second row up in matrix A is now the fourth row, and the fourth row in matrix A is now the second row. So all they did was switch rows. So matrix A, they switched row 2 and row 4. And remember, that gives me the opposite determinant. So the determinant of this new matrix will be negative 606. All right, and then this last one. Now the first, second, and third rows are the same. The first row, second row, and third row are the same as these. This last row, 0, 0, 2, 11, how would I get that? Well, that would just be simply adding row 1 to row 4. If I added row 1 to row 4, you see I'd get a new row 4. 3 plus negative 3 is 0. 6 plus negative 6 is 0. Negative 1 plus 3 is 2. 5 plus 6 is 11. So that was the operation of taking a multiple of row 1, so just 1 times row 1, and adding it to row 4. Remember that when you take a multiple of one row and add it to another row to create a new matrix, it doesn't change the determinant. So that last one there would have exactly the same determinant as the original of 606. And again, you see row 1 was added to row 4. All right. So now, using this concept, the fact that these row operations, change the determinant in some way, have an effect on the determinant, gives us an opportunity to find the determinant of a matrix in a different way, using row operations instead of cofactors. Right? Remember, last section was cofactor expansion. So you see what's going on here. Now they do this 4 by 4, and I'll let you read this one. So they start off with A, and they say let this triangle shape, this delta, let's suppose that represents, let triangle be the determinant of the matrix at each step. All right. And then at the end they solve for the determinant of A, the determinant of the original matrix. Right. So you see what's going on here is, they mention, hey, remember that a matrix that's in echelon form is triangular. Right? If you have a matrix in echelon form, it's going to be upper triangular. And if you recall from section 4.2, a triangular matrix has a very easy determinant. Right? The determinant of a triangular matrix is just the product of the main diagonal entries. So our goal is to perform row operations to get our matrix into a row equivalent matrix that's upper triangular. You see this last matrix here has zeros all below the main diagonal. It's upper triangular. And then also keep track. That's what they're doing off to the side here. Keep track of how the determinant is affected, and then solve for the original determinant when you're done. All right. So I'm going to be doing this. Right, again, you can read through their example here. I'm going to be doing this with a little bit smaller one, right? They have a 4 by 4 matrix up here. I'm going to do the same thing with this 3 by 3, where we're going to use row operations to kind of, transform it into an upper triangular matrix, put it in echelon form, and then figure out what the determinant of the original matrix must have been. Okay, so here's this 3 by 3 matrix, and I made this little note off to the side like they had in their example prior. I'm going to let this little delta shape, this triangle, represent the determinant of the new matrix that comes about in each step. All right, so I'm going to use row operations. I'm going to put this in echelon form. That's the goal. I'm going to go through elementary row operations to put this in echelon form, or row echelon form as they call it. Don't worry about reduced. I mean, you can go to reduced. I mean, that wouldn't be wrong. It's just you don't need to do all that. Right? You don't need to do all that work. Just go one step at a time until it's in echelon form. Make it upper triangular, and then you'll be fine. Okay. So right now, at this first step, the determinant of this matrix is just whatever the determinant of A is. Right? We don't know the determinant of A. Okay. So again, triangle is going to represent the determinant of each new step. All right. Now the first operation I'll perform is, remember, I like having a pivot. That my first pivot up here, the new pivot, I like it having being a 1. I like it to be 1. So I'm seeing this 1 down here in the third row. So I'm going to switch the first row and the third row. So I'm going to switch row 1 with row 3. All right. And that'll create this new matrix where you have 1, 4, 0, negative 1, 1, negative 1. And then the third row is now 2, 4, 1. Right. Now, again, the little triangle represents the determinant of this matrix is represented by the triangle. Now, remember, I switched rows. So the determinant of this new matrix will be the opposite of the determinant from the previous step. So the determinant of the previous step was, the determinant of A. The determinant of this step's matrix will be the opposite of the determinant of A. And again, that's because I switched 2 rows. All right. Now, I'm going to take this pivot of 1 here. Right. I want to get zeros below. Right. I want to start putting this in echelon form. Now remember, if you multiply a row, if you add a multiple of a row to another row, it's not going to change anything. It's not going to change the determinant. All right, so I'm going to do those multiple. When I add multiples of one row to another row, I can do multiples of those at the same time. So I could take row 1 and add it to row 2, right, to get a new row 2. That'll make this entry a 0 here. And then I would take negative 2 times row 1 and add it to row 3 to get 0 in the third row first column. So negative 2 times row 1 plus row 3, right, to give me a new row 3. And again, I'm doing both of these at the same time because this operation, adding a multiple of one row to another row, doesn't change the determinant. So I don't mind doing both of those at the same time. All right, so row 2 and row 3 are going to change. Row 1 stays the way it is, 1, 4, 0. And then I'll do row 1 plus row 2. So 1 plus negative 1, 0. 4 plus 1, 5. 0 plus negative 1, negative 1. And then I'll take negative 2 row 1 plus row 3. Negative 2 plus 2, 0. Negative 8 plus 4, negative 4. 0 plus 1, 1. Okay. All right, so I've got, pivot 1. It's all zeroed out underneath it. Okay. Now the determinant of this matrix, again, triangle will represent, now the triangle represents the determinant of this matrix, is going to be exactly the same as in the last step. All right. And maybe I could even put the step numbers, triangle 1, triangle 2, triangle 3. Triangle 3, the determinant of this third step, since I only did this operation twice, I just added multiples of one row to another row, it's going to be the exact same as triangle 2. Right? It's going to be exactly the same as the previous step, which was the opposite of the determinant of A. Right? Okay. All right, and then I really only have to do one more thing. Now, I know I said I like having pivots of 1, but in order to make this echelon form, in order to have this be upper triangular, the only thing left to do would be to make this -4 into a 0. So I'm going to do one more step here where I take a multiple of one row and add it to another row. So I'm going to take, 4/5 of the second row, because that'll make that into a 4, and then add it to the third row, which would make this into a 0. So I'm multiplying the second row by 4/5, adding it to the third row, and that'll create a new third row. So first row is the same. Second row is not changing. It's this third row. So 4/5 times 0 plus 0 is 0. 4/5 times 5 is 4, plus -4 is 0. And now you see I'm going to have echelon form here. This will be an upper triangular matrix. And then -4/5, right? -4/5 plus 1 would be 1/5. Right? So, oh man, I got a fraction here. Now, I mean, if you don't like the fraction, you can multiply the last row by 5, but I'm good. Right? This is in echelon form. Right? This is in echelon form. Also, it's upper triangular. Right? All the entries below the main diagonal are a 0. That was my goal. Upper triangular. And upper triangular matrices have easy determinants. Now, I'll call this triangle 4. All right, let's say triangle I in each step I. Right? So the determinant of this fourth matrix here. Again, all I did was took the third matrix, added a multiple of one row to another row. So it's going to be exactly the same as triangle 3. It's going to be exactly the same as the determinant of the matrix above it, which we saw was exactly the same as triangle 2, which was the opposite of triangle 1. So it was all equal to the opposite of the determinant of A. All right. Now, this determinant for this triangle 4, the determinant of this fourth matrix, I know, because it's upper triangular. It's 1 times 5, 1 times 5 times 1/5. So 1 times 5 times 1/5 is the opposite of the determinant of the original matrix. And then I solve for the determinant of the original matrix. And now 1 times 5 times 1/5 is just 1. So 1 is the opposite of the determinant of A, meaning that the determinant of A, the determinant of my original matrix, must be -1, right? If 1 is the opposite of it, then it must be -1. So again, following the procedure, getting it in echelon form, making it upper triangular. All right, so back here, filling this in, the determinant. Now you could also check it another way, right? Do cofactor expansion. Since it's a 3 by 3, you could also do that method where you copy the first two columns and then do those, down to the right diagonals, add those up, and then subtract the down to the left diagonals, but you should get -1. All right, you see they do basically the same procedure I went through. All right, so I'm going to do that one more time. All right, I'm going to do that one more time. Okay, but this time the only operation I haven't done yet is the multiplying a row by a number. So I'll do that operation this time. All right. So, I guess instead of the triangle stuff, maybe I'll call this B, and I'll call the next matrix B1 and the next matrix B2, because they're going to be different matrices, right, when I perform these operations. Just know that this is B, and all the other B's I write are going to have a subscript, and it'll be different. All right. So right now, this has a determinant of B, right? I don't know what the determinant of B is, right? This is equal to question mark. I have no idea. Now let's perform an operation. All right, I want to again put this into echelon form, make it an upper triangular matrix. And usually that upper left corner there, right, the first pivot, I want to be a 1. Now I could switch rows and then multiply that row by 9, but I'm going to do that thing where I multiply the top row by a half. Right? That'll get a 1 here. That'd be nice and easy. So I'm going to multiply the top row by a half. Right, so I'm going to take half of row 1, and that'll produce a new row 1. All right, and that'll create this new matrix, which again I'll call B1. All right, B1 is totally different than B. And this new matrix, I'll do half the first row, so 1, -1, 2. And then you got -1, 1, 0, and 0, 3, 1. The other two rows are the same. Now the determinant of B1, right, the determinant of this matrix, because I multiplied the first row, I multiplied the first row here by a half, it should be half of the determinant of the original. I multiplied a row by a half, so I multiplied the determinant by a half. Okay. Then I'm going to try to zero out the stuff below it, right? So I got 1 here, -1, and just add the first row and the second row. And the bottom of that column is already a 0, so I don't need to do any more than that. So I'm just going to go row 1 plus row 2 and create a new row 2. All right, so this will create matrix B2. So the only thing that's changing is row 2. So row 1's the same. Pardon me. Row 3 is the same. I'm just adding the first two rows. 1 plus -1 is 0. -1 plus 1 is 0. And 2 plus 0 is 2. Okay. Now, because I just did that, adding a multiple of one row to another row, the determinant's not changing. All right, so the determinant of this second matrix, B2, should be exactly the same as the determinant of B1, right, the one before it, and we said that that was equal to half of the determinant of the original. All right, so the determinant of this matrix is also half of the determinant that we want. All right, and then I see one more thing I can easily do to put this in echelon form. Just switch row 2 and row 3. Watch. Right. So if I just switch row 2 and row 3, I'll get a new matrix, which I'll call B3. So the first row is the same, and then I'm switching row 2 and row 3. So I got 0, 3, 1 now as the second row, and 0, 0, 2 as the third row. And do you see that this B3 matrix is in echelon form? It is upper triangular. And the determinant of this new matrix, this B3, should be equal to the opposite, right? I switched 2 rows. So it should be the opposite of the determinant of B2. Right? It should be the opposite of the determinant from the previous step. And we said the determinant from the previous step is half the determinant we want. So this is negative, and then half of the determinant determinant of B. So the determinant of this final matrix is negative half times the determinant that we want, the determinant of the original matrix. Now this final matrix is upper triangular. Right? So what is the determinant of B3? What is the determinant of this final matrix? It's 1 times 3 times 2, it's 6. So 6 is negative half times the determinant of B. All right, and then we solve for the determinant of B. That would just multiply by negative 2. All right, so the determinant of the original matrix must be negative 12. All right, so back to the top here, the determinant must be negative 12. Now you can double check, this is a 3 by 3, you've seen other ways to do it. Do cofactor expansion, or because it's a 3 by 3, you can do that other method with the copying the first two columns, but again, that's only for 3 by 3s. And see that this is negative 12, right? So back here, negative 12. And again, I think they pretty much do the similar steps that I do. All right, now some additional properties of the determinant. So the determinant has the following properties. So suppose A and B are n by n square matrices, and K is any scalar. All right, if A has a row of zeros or a column of zeros, then the determinant of A will be 0. Now you've seen this already. Remember cofactor expansion. You can go down any row or any column. If there's a row made up entirely of zeros, or a column made up entirely of zeros, and you perform cofactor expansion down that row or down that column, the determinant will be 0. So that one was something you already probably could figure out on your own. Number 2. If A has 2 identical rows or 2 identical columns, then the determinant of A is 0. Think about that. We talked about how the row operations affect determinants. If 2 rows are exactly the same, then I can take negative 1 times one row, add it to the other row, and then that other row would become a row full of zeros, and then you'd have situation number 1 again. And remember, when you add a multiple of one row to another row, the determinant is not affected. So if I can make a row full of zeros or a column full of zeros, then that determinant would be 0. If A has 2 rows or 2 columns that are scalar multiples of each other, right, then the determinant of A is 0. Again, that's kind of similar to number 2. If you can, take a multiple of one row, add it to another row, and get, a row of zeros, or a column of zeros, you can do the same thing with columns, right? You'll see down here, you can see that you do the same thing with columns that you do with rows. Then the determinant will be 0. Right. Here's a nice property. The determinant of the product of 2 matrices will be equal to the determinant of the first matrix times the determinant of the second matrix. Okay, so that's nice to know. And this is going to help us out too when we talk about the determinant of an inverse. Right, if we know the determinant of a matrix, we can easily find the determinant of its inverse using this property here. We'll see that later, not in this section. The determinant of a scalar times A is that scalar to the nth power, right? This is an n row, n column matrix times the determinant of A. This again comes from our row operations. Remember, if you multiply a matrix by a scalar, you're multiplying every single entry by that scalar. So that would mean you're multiplying all n rows by the scalar k. And you saw earlier, if you multiply just one row by k, it multiplies the determinant by k. Well, here you're multiplying all n rows by k, so that's why the determinant of A is multiplied by k to the nth power. Times k times k times k times k, for one for each row. And finally, the determinant of A transpose is equal to the determinant of A, and hopefully this makes sense too because of cofactor expansion. Remember, if you want to find the determinant of a matrix, you could do cofactor expansion down the first row. Well, if you do that, if you look at A transpose and do cofactor expansion down the first column, it'd be exactly the same thing. Because remember, the rows of A are the columns of A transpose. So their determinants should be exactly the same. All right, so the transpose of a matrix interchanges the rows and columns. We've seen the transpose before. So thus, an important consequence of the property determinant of A transpose equals determinant of A is that the effects of row operations on the determinant applies to columns as well. All right, because if you perform row operations on A, that's exactly the same as performing column operations, right, where you maybe switch two columns or add a multiple of one column to another column or multiply a column by a scalar. Doing row operations on A is exactly the same as doing column operations on A transpose. So all the properties I mentioned earlier involving row operations are exactly the same if you were to do it to the columns. So I'll again show you an example with a little 2x2 matrix. So if a multiple of one column is added to another column, the determinant won't change. If two columns are switched, exchanged, then you get the opposite determinant. And if a column is multiplied, if one entire column if every entry in a column is multiplied by k, then the determinant of the new matrix is k times the determinant of the old one. So again, an example where this with all these happening. All right. So again, here I have that simple 2x2 matrix that I had earlier. 1, 2, 3, 7. The determinant is 7 minus 6. Right? The determinant of this matrix is 1. All right. So now we're going to look at the columns. So this is column 1. I'll call it C1. This is column 2. I'll call it C2. All right. So instead of R1, R2 with the rows. And I'm going to perform operations on the columns now and see how the determinant is affected. All right, so the first of those they mentioned was, if you take a multiple of one column and add it to another column to create a new matrix, a new column, the determinant won't change. Let's see that. Let's say I took 5 times the first column, column 1, and added it to column 2 and created a new column 2. So again, it works exactly the same way as your row operations. Now this will create a new matrix. So I'm starting with matrix A. I'm starting with matrix A here, and I'm performing this operation to create a new matrix called B. Now I'm only changing the second column. So the first column with 1, 3 stays the same. And now let's say I multiply the first column entries by 5 and then add them to the second. So 5 times 1 is 5 plus 2 is 7. Makes a new column 2 entry. 5 times 3 is 15 plus 7 is 22. Alright, so now I have this new matrix with a new second column after adding a multiple of one column to the second column. Now what is the determinant of this new matrix? It's 22 minus 21, which is still 1. See, it's exactly the same as the determinant of the original, of the previous step. So adding a multiple of one column to another column also doesn't change the determinant. The second one was switching columns. All right, so let's say I have matrix A, and then we perform the following operation, where I switch column 1 and column 2. And then I'll create a new matrix. Again, I'll call it B. Now if I switch the columns here, we'll have 2, 7 is now the first column, and 1, 3 is now the second column. And what's the determinant of this new matrix? That would be 6 minus 7. That's negative 1, which is the opposite of the original determinant. Okay, so switching two columns gives you the opposite of the previous determinant. And finally, the other operation it mentioned was you know, multiplying a single column by a scalar. So again, say I start with matrix A, and I'm going to perform the following operation. Let's say I multiply the first column by -3. So I'll multiply the first column by -3 to create a new column 1. All right, so -3 times column 1 gives me a new column 1, and I'll create a new matrix. Now I'm just doing, -3 times the first column entries. So that'd be -3 and -9. And then the second column did not change, so 2, 7. And then I'm asking, what's the determinant of this new matrix? Well, that'd be -21 minus -18. So -21 plus 18, that's -3. And you see that that's just -3 times the original matrix, or times the determinant of the original matrix. Okay. So if I multiply a single column by a scalar, the old determinant gets multiplied by that scalar as well. Okay, so the same stuff applies for column operations as it did for row operations. Right, and that's because the determinant of the transpose would be exactly the same as the determinant of the original. So doing row operations on the original would be exactly the same as doing column operations on the transpose. So that you can do it to either, right? Because every the A and A transpose are transposes of each other, if you want to say it that way. All right, so that was an example of that. Now look at this example here. So again, this is focusing on maybe some column stuff, or some of these other properties that were mentioned. Right. So same, I'll read through this one. So you have the look at the columns. Again, they tell us that the determinant of this matrix is 40. Now, look at how this one compares to this one. So this one, the first column is the first row. The second column is the second row. The third column is the third row. This matrix is just the transpose of this matrix. And the determinants of transposes are the same. So matrix A here has a determinant of 40. And they talk about the transpose 40. All right, look at matrix B compared to this one. Now, they have, let's see, it looks like they just switched the first two columns, right? Column 1 in the original is now column 2, and column 2 in the original is now column 1, and column 3 is the same. So they just switched two columns, and that gives you, remember, the opposite determinant. So the determinant of B is -40, and they explain that here. And then this last one, the first column's the same, second column's the same. All right, so they got the third column somehow. All right. So what would they have done? So it looks like they have 3, 4, 3. This is 0, 0. I guess they would have taken a multiple of column 1 plus some multiple of, plus column 2. To get the new column, or plus the column 3. Oh, they just they just added column 1 and column 3. Yeah, column 1 plus the column 3 entries to get new column. 3 plus 0 is 3. 1 plus 3 is 4. 5 plus -2 is 3. So yeah, they just added column 1 and column 3 to get the new column 3. So remember, when you add a multiple of one column to another column, it doesn't affect the determinant. So this C here would also have a determinant of 40, and they explain that there. All right. So here they tell us this 3 by 3 matrix has a determinant of -120, the way it looks right now. All right, this one's a joke because, look, the second row is all zeros. So the determinant of this matrix is 0. This one, every single row is the same. And when you have two rows that are the same or two columns that are the same, you also have two, every column is just a multiple of each other. The second column is just twice the first column. The third column is just three times the first column. So if you have rows that are exactly the same or columns that are multiples of other columns or whatever, something like that, the determinant will be 0. All right, now this third one looks a little different. Let's see, compare that to the first one. Yeah, it's just the transpose. Right, the first row up here is just the first column here. The second row up here is just the second column here. And the third row up here is the third column. So this has a determinant exactly the same as the original one, negative 120, because they're just transposes. And I guess I'll leave the fourth and the fifth one to you. All right, and then this one has there's 6 of these, sure. Find the determinant. Now this one's pretty obvious. The second level. Let's see what the second level looks like. So another determinant. Oh, look. Look at this. Look at this hint. Oh my goodness. Third level. Alright, now see they tell you the determinant of this matrix is 6, and now I know you know how to find the determinant of a 2 by 2 pretty easily, but just compare them, and what would be the new determinant. Fourth level, something similar. Fifth level is something similar, but with 3 by 3s. And then the sixth level is again something similar, but with a 3 by 3. All right, and then you have your additional exercises. Again, some of these are on assignment 6, some are not. I would still recommend that you try everything, try them all. And you can view the solutions to check yourself. And I say this every time, please try to work out the problems, try to figure out what you're doing before you look at the solutions, right? Just use the solutions as a guide. Do not rely on them. Do not just copy them. You're not going to learn anything that way. All right, so that's it. Properties of determinants. Hopefully this is a good guide for you when you work through section 4.3 on your own. And let me know if you have any questions, of course, and thank you very much for watching.